All right, cool. So, super exciting to see GPT-5 come out. Today, we're going to talk about the other end of the spectrum. We're going to talk about small models, and in particular, Google's Gemma 3N, and some of the decisions they made in order to get this as small as possible. Presumably, the goal being to get it on your Android phone, to get it down to that size. All right, so as usual, this will be sort of a free-form discussion. I don't have slides, and so we can kind of go into more depth or less depth. Everyone should feel free to ask questions. So I think it was about a month or two ago that they announced the 3N model. And let's see here, where's the other page I wanted to show real quick here. So if you go to like this page that Google has, they say, okay, there's some things about it. This model's optimized for use in everyday devices. And so they say, hey, it can handle audio, it can handle images and video, it can handle text. They've got a new vision encoder. They do this PLE caching thing, this per-layer embedding thing, the MatFormer architecture. So there's a archive paper for this Matryoshka transformer architecture. This conditional parameter loading is actually fairly straightforward. It's just if you're doing text only, don't bother loading the vision encoder, right? Lots of language support and pretty decent for a small model, 32,000 token context. So that's a super high level, but not all of this is stuff that we talk about all the time. Not all of this makes sense. So I wanted to kind of just dig into it a little bit more. So if I flip over to this here, there's this one diagram that they show. And so if this is the standard full Gemma 3N model, they have the main LLM that we're all familiar with, and they say this is just under 2 billion parameters. The vision parameters, this is basically the image encoder, okay? The audio parameters, this is so it can do speech to text. And then they have this other part, which is we'll talk about a little bit, is this new per-layer embeddings. It's actually quite large if you look at it, right? It's even bigger than the LLM. Whether the size of this does not necessarily correspond exactly with its its power. They basically kind of we'll get to it, but basically they have a very low compute way in which they use these parameters, and so the number seems really large, but it's not necessarily providing as much horsepower as if they just threw more into the attention and the MLP in the core LLM. So the core LLM may have some interesting things, but there's not too many details that they give about this. We'll go over a few of them. But the key thing is they say if you're processing text only, then this stack remains the same, okay? But we're going to use this dark blue part, which is the main LLM. We don't need to load the vision encoder. We don't need to learn the audio encoder. And then the key thing is this large chunk of information that's in these per-layer embeddings in the PLEs. These actually are managed by the CPU. And so whatever kind of GPU, it's not necessarily like an NVIDIA GPU on your phone, but whatever the GPU is that's doing all of your matrix multiplies and all of your stuff like that, does not need to worry about this massive amount of parameters, and those will get fed in when it's processing the different layers of the LLM. So this means that your GPU floating point effective size is under 2 billion. So you can see if you add up all of these, I think it adds up to around 5 billion. And so this is why they're saying that, hey, this is 5 billion, but it's effectively only 2 billion. And so when you see the naming of these models, if it says like E2B, the E is the effective. Um, little bit of marketing there because if you want to process audio, then you're still using this E2B model, but you actually do need a little more memory. You need another 0.68 because that part needs to be loaded. So um, fair enough. All right. So yes, so the one thing they tout is this conditional loading of the vision and the audio encoders. I don't think there's really any fancy logic going on here. In almost every multimodal model, there is a component that's the base LLM, and there's a component that's a separate encoder and sometimes decoder um, for images, for audio, for whatever. So if you know you're in a text-only environment, it's a pretty straightforward thing just to say, don't load, don't waste the memory loading these other encoders. Any questions so far on that part? All right. So let's talk about these per layer embeddings and the per layer embedding caching, PLE caching. I haven't looked super recently, but when 3N first came out, there just was not a lot of information available as to what exactly they were doing. So most of the stuff that I've seen is where people took the computation graph um, for 3N and they basically just reverse engineered it. And they saw like, okay, it's doing this add and then it's doing this multiply, it's grabbing this matrix, this is the size of it, blah, 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 blah. And so reverse engineering, basically, this is what we know about the PLE caching. Um, so overall, like I said, the Per-Layer embeddings, they say are cached to fast storage. The main thing is they're handled by the CPU and they're going to get delivered to the GPU just in time as each layer is getting processed. So Gemma 3N has 30 layers, and so there's 30 of these PLEs, and each one, as the GPU is processing layer one, and then layer two, and then layer three, it's going to need, and so the CPU can work in parallel to grab the PLE and then, if necessary, if it's not shared memory, copy it over to the GPU so that when the GPU wants to uh, do the calculations for layer two, the PLE for layer two is just sitting right there in GPU memory. So what you do need is a very, very small amount of memory to hold the actual embedding. Um, so if you want the embedding for the current token, it turns out that that's minuscule. It's tiny. It's 256 dimensional. So it's just 256 floats. It's not even 1K of memory. And so that's why they don't include that in anything. They basically, in this diagram, they basically treat it as a zero. And that's reasonable enough. So it's pretty amazing that they have over 2.5 um, billion parameters here, but the amount of GPU memory you need to process all of this is really only 256 at a time. It's basically nothing. So what are they doing with these per-layer embeddings? I don't know if I fully understand it. So if any of you guys have seen anything, if you're more familiar, please chime in. Uh, but basically, the way it works is in a regular LLM, you have your input token. So if the word is boy, then boy gets embedded into a dense vector of floats, and then it goes into the first layer of the model. That layer has attention, has MLPs, and then out of that layer um, is whatever the computed output is, and that gets added onto the residual stream. And then layer two kind of works in a similar way and whatnot. Okay. Um, the input for layer two is based on the output from layer one, and at that point, there's no direct connection to whatever your initial token was anymore, the word boy. Obviously, the information coming out of all the layers is very much based on the fact that that was the input. But if you're looking literally at the input for layer 11, it's the output from layer 10, and the fact that the original token was boy doesn't matter anymore. It's irrelevant. right? The way the PLEs work is different. All of the embeddings for each of the 30 layers comes directly from the input token. So basically, if the current token is boy, and the vocabulary size for Gemma 3N is about 260,000. Okay, it's this number over here. Oops, that was not what I wanted to do. So there's 260,000 embeddings for each of the layers. Okay, and they all come from that token. So in the case of if your input current word is boy, then the CPU has to say for the first layer, what is the embedding for the token boy, and it has to copy that to the GPU, and then it can say, okay, what is the per layer embedding for the for boy for the second layer? What's the embedding for boy for the third layer, and so on and so forth, and keep feeding that in fast enough to keep up with the GPU. If you have done like machine learning and coded stuff up, when you have something like this, we use these one-hot vectors. So if boy is token 17, you don't use the integer 17. Instead, you use a vector that's 260,000 long, and it has 16 zeros, a 1, and then 200,000 more zeros, right? That one hot vector then gets multiplied by the embedding matrix, and um, and what you get then is your input embedding. In the case of Gemma 3N, the model dimension is 2048, and so the embedding matrix is a 262,000 by 2048 weight matrix. When you're doing things on the CPU, you don't have to do one hot encoding, and you don't have to do a matrix multiply. If I asked you for if we weren't talking about GPUs or whatever, if we were just talking about an array of strings, and I let's do something easier. Let's say an array of integers. If I asked you for the 17th element of that array, you just do pointer arithmetic. Okay, so if the integer is 4 bytes, then you just basically say, here's the beginning of my array. 17 times 4 is, what the heck is it, 68? So you add 68 to the beginning of your array, and then that's the pointer to the 17th entry. So that's what winds up happening when you do this embedding business. Is they say, oh, it's this 2.55 billion parameters, but what you're gonna do is you're gonna store them in contiguous memory, and it's just gonna be an array, and you're just gonna access it that way. So no matrix multiplies, no calculations need to be performed by the CPU. The CPU just has to do pointer arithmetic in order to get to the right entry. And so if your vocabulary word 100,000, again, it's just going to do pointer arithmetic, and it's going to go straight to the 100,000th entry, and it's going to read those 256 floats from there and copy them over to the GPU. So that's basically the first half of the per layer embeddings. I haven't said anything about what the model does with those embeddings once it gets there. But any questions about how, like, from the CPU perspective, it's just array indexing, and it's super fast. It doesn't require any matrix multiplies. Good? Yeah? All right. So then, not 100% sure what's going on with what it's going to do with this embedding. Basically, if you look at the computation graph, what we see is the regular layer does its thing. So there's the attention layer and the MLP layer. And then coming out of that layer, you have the output of that model. What we see is that another thing that's happening is that the inputs to that layer are getting projected down from 2048 to 256 dimensions. So it's getting projected down by a factor of 4. Then what they do is they take this this shortened vector of 256, and they element-wise multiply it by the per-layer embedding. So a very simplistic thing that the per-layer embedding could do with this whole business is you could have, say, for example, I'm somewhat dramatically oversimplifying this, okay? But you could, for example, have one floating point number be, is this a noun? One floating point number could be, is the current word a verb? Is the current word an adjective? Okay. And if it's the word boy, then it is a noun, and so you're going to have sort of a one in the first floating point, and you're going to have zeros in the other locations. So if this per layer embedding was just a bunch of ones and zeros, and you element-wise multiply them, then effectively what you're doing is you're just doing a gating operation. You're keeping some of the values and you're just blocking the other values by zeroing them out. Okay? Because we're doing this projection down to 256, and then I didn't mention it yet, but then we project it back up to the full model dimension 2048, and we add that in with all the other outputs. So effectively, what this allows you to do is it allows you, in this first projection down to 256, you're doing a matrix multiply, and it allows you to pick the presence of up to 256 different directions, okay? Not to go deep into the whole mechanistic interpretability, but if most of the information inside an LLM is stored as directions, and the residual stream is considered a vector space. So maybe, this direction has to do with um, um, sorry, I'm trying to think of like some good examples here, but I'm blanking a little. But like how much the current topic is male versus female. Okay. And then maybe there's a direction associated with the color red. And maybe there's a direction associated with old versus young or something like that. Okay. So when you do a matrix multiply, right, you basically have like 256 columns in your matrix. And so each of those can be a certain direction, and you can basically test by doing this matrix multiply, you're effectively doing a dot product of the input with each of these 256 columns. And so that dot product is essentially going to be a large number if we have a component in the direction of that column, and it's going to be close to zero if you have nothing in the direction of that column. So I know this is not necessarily the way we typically think about what is a matrix multiply or what is a down projection, okay? But in this case, I think that's probably the most intuitive way to think about it, is that this down projection from 2048 to 256 allows us to test for the presence of 256 unique directions. And one of those directions might be, is it a noun? Is it a verb? Is it male, right? And then by doing this element-wise multiplication with the embedding, that allows us to gate this information to say, well, I don't want all of this information. I'm only interested in certain information based on what the input word is. So if the input token is boy, you might do gating where you allow certain things through, but if the token was run and it was a verb, then maybe you do a bunch of different things that you allow through. And there's 30 layers, so there's 30 times that you really have the option to do this special kind of a thing, and so that just gives the model a little bit more horsepower. I don't think that this, gated 256 dimensions is terribly powerful. It's a lot less powerful than the MLP layers. It's much, much, much less powerful than the attention layers. But it is a little bit of extra juice that you can give the model, and the point here is that it requires fairly little computation, and it doesn't require any more GPU memory because of this scheme that they use to have the CPU manage all of the embeddings instead of it being, if you just had a normal, you know, uh, um, linear perceptron type layer, then you're soaking up a lot more GPU memory. All right, so that's the gist for the PLE caching. It's the most mysterious thing that I see in Gemma 3N, and it's uh, um, people have been playing around with this stuff, but this is really the first time I've heard about anybody using it for real, not just, to publish a research paper. So I'll pause here. Any questions about the PLE, um, the embeddings and the PLE caching?
I have a question, Pat, if you don't mind.
Yeah, please fire away.
Yeah, maybe my ignorance or maybe I missed what you said, but is when they go from the larger and project down to the smaller matrix, do they predetermine what that matrix is going to be, or is it like a convolution network where the model just kind of as it trains it, it kind of figures out its own patterns, and then they have to kind of like reverse engineer it to see what happens with it?
Yeah, yeah. So all of this is trained. So that down projection by a factor of four is going to be learned weights, just like in a CNN, and the embeddings at each layer for each input token are also learned. So I'm just making up things like maybe it cares if it's a noun, maybe it cares if it's a verb or whatever, but it's going to learn and so it's just going to have a little bit of horsepower to, in addition to the attention and the MLP, to have a little bit of extra information at each layer at its disposal if it wants to.
Okay, thank you. That answered my
Yeah.
question.
Yep. Yeah. Thanks. That was a great question. Yeah. So as far as I know, all of these are learned and they're all trained simultaneously with each other when the model is trained.
I guess it
All
would
right.
really suck if the model came out trained poorly. All the compute power and stuff that they had to do. Because if it's
Yeah.
if it's just like any other neural network, you always get that chance. So it's just it didn't work out, you know.
Yep.
A lot of
Yeah.
computational power.
Um, they say that there's per layer embeddings for every layer, for all 30 layers, okay? For example, I'm somewhat skeptical that the very last layer, the 30th set of per layer embeddings, I doubt that one's doing very much. Okay. Like early on, you're kind of figuring out what the word is, and if you have a compound, I don't know, is that the right compound word, but whatever. If you have like Golden Gate Bridge, New York City, and there are multiple tokens, it does this thing that um, researchers are calling detokenization, where it turns the multiple tokens Golden Gate Bridge into one internally one entity,
Yeah.
right? Um,
That's kind of what
it's doing
engrams do in NER, isn't it?
Yeah, exactly. So it's
Yeah.
like named entity. So it's like I use proper nouns like Golden Gate Bridge. So it's doing named entity recognition and probably some other things as well, because maybe like how in English you would say like I walked the day before that I had walked. It's still two words, but it's probably combining that into one semantic concept. Okay. So the first couple layers are doing this detokenization thing or whatever, and then we know there's like factual recall happening in the middle and some other things happening, whatever. But basically, by the time you get to the last two layers, it's really just finalizing its next token prediction. And I don't think at that point, knowing that the input token was boy is really all that helpful. Um, so my guess is they probably could have said instead of having per layer embeddings for every layer, they could have gotten away with just doing the first 90% or something. But my guess is at this point, if you're going to do it like, it actually would be more effort to customize the last few layers to look different than the first ones, whatever. And so, six one half dozen other, they probably just did it for every layer. But to your point, like some of this is helping more than others, probably. Cool. All right. So I'm going to move on to the MatFormer, and this is probably one of the more interesting, most talked about things that they did in in Gemma 3N. So in 3N, uh, by using this technique, what they did is they trained smaller versions of the model, And by smaller, basically what I'm saying is that they had smaller weights, so less horsepower, less capacity of the model. Um, but people have been doing this for a long time, right? For llama, they say, oh yeah, we have our whatever 70B model, we have our 8B model, we have our 2B model. There's different sizes of the model that have different. In this case, though, what's interesting about this is that they're training these smaller versions that all have the same number of layers and everything. The difference is that the weight matrices are smaller, and they're not training a separate version. They're training these different sized models simultaneously. So by the time they're done training the whole thing, they basically have a full-size model and they have a half-size model. And in the paper, they had like a quarter-size model, all coming out of just this one training. So if we flip over to the paper, and again, depending on like how many questions you guys have, we can spend more time or less time on this. Um, but the key insight is in this diagram, and it's actually not the whole diagram, but just this part on the left. Okay. The idea is that this yellow rectangle represents one of the weight matrices. So let's say the matrix that allows you to calculate the queries in an attention layer. All right. So for their full-size model, they say that this weight matrix, let's say, has 256 columns. They say, but if you only use the first half of it, you'll only have 128. And if you only use the first quarter, you're only going to have 64. And if you only use the first eighth, you're going to have 32. Um, and crazy enough, what they do during training is they just have a random number generator and they do things batch at a time. But so they say for this batch of inputs, we're going to roll the dice and see whether we want to use all of the weights, only half, only a quarter, or only an eighth. Um, and the different sizes never explicitly talk to each other. Okay, so the quarter size model never talks to the half size model. The eighth size model never talks to the full size model. But for say the quarter and half size model, half of the weights, half of the parameters are identical. So if you do a batch that's using the quarter sized, and then at the end of your forward pass, you're now going to do back propagation. You're going to update your weights, right? So it's actually updating half of the weights that the slightly bigger half size model uses. And because of that, early on, you could get a little bit of a tug of war where the quarter size model is pulling one direction, the half size model is pulling another direction. But eventually, in order to get low loss, like we do when we train these models, the only way in which you can get really good low loss, not just on the eighth size batches, but also on the quarter size batches, is if the eighth and the quarter size batches sort of are working in harmony. Okay, and I don't think you should take this argument too literally. Okay, but essentially, what they're saying is that the most important thing. So let's say we're looking at the weights in layer two. The most important things that must get done at layer two are going to be in the 1/8 sized model's weights. They're going to be in the first little bit, the first little 1/8 of the weights. And then the next most important things it needs to do will be in the quarter size. And then the next most important things will be in the half sized. And the least important things that it needs to do are going to be in the rest, in the bottom half of the weights. Okay. So like you could imagine, knowing is this word a noun or a verb might be in that first 1/8. knowing is this word singular or plural? Is it duck or ducks? That might be in the first 1/8, okay? But like the nuance between different words that are colors that are shades of green, that might not be something the model can actually handle in the 1/8 or quarter size or whatever. That might actually be, towards the end of these weight matrices. So the cool thing about this is that even though the different size models never explicitly talk to each other, um, they're all running batches independently from each other. Just by virtue of the fact that they share weights, this phenomenon seems to happen. And so what that means is that it's a little bit like when you do quantization, okay? You can have a 16-bit floating point number. If you quantize it to 8 bits, you have some rounding errors, but the number is largely the same, okay? You quantize it a little further to, 4 bits, and now maybe you have some fairly large rounding errors, but again, the number is still the same. Effectively, that's what they're saying that this Matryoshka, this MatFormer, was able to do. It was able to say that you can think of the innermost, this 1/8, red part, as being the most important part, largely the same, just with a bunch of rounding errors. And so the blue has some small rounding errors compared to the full yellow. The orange has some slightly bigger rounding errors, and the red has even more rounding errors, but they're not actually doing different things. If you look at a llama, 7 billion and a llama 30 billion that were trained completely separately, they're not doing the exact same things in the exact same places. We know that there's certain patterns that they all learn identically in terms of like, they know the difference between a noun and a verb, but they're not happening in the exact same way in the exact same place. In this case, these models are, I'll use the word coherent enough that they're doing the exact same thing in the exact same way. So if, if in the full size model, you have a large number in the third floating point number at layer 2, whenever it's a noun, the 1/8 model has that same pattern as well. So, so it's kind of really interesting that these models are so coherent. And what they don't say in the paper is I'm pretty sure the full-size model takes longer to train because you're splitting between batches that are half, quarter, eighth size. You're not always doing full-size batches. Whereas if you were just training the yellow model, I think it would train a little bit faster. But it's probably fair to say, I haven't dug into the details, that training this nested Matryoshka model is faster than training 4 separate models, training a yellow model, then training a blue model, then training an orange model, then training a red model. Okay, so it's a little bit more work than training just the yellow model, but it's less than training 4 completely separate models. And remember, these models, today are being trained on, approximately 10 to 15 trillion tokens. And so that's the thing that you don't want to repeat um, 4 times. All right, so this is the first part, focused on the training and then how you get these coherent weights. Let me pause here. Any questions about this strategy of subdividing your weights into smaller pieces? All right. Um, so then what does that mean you can do after you've trained this? Well, typically, if you wanted to have, say, a llama 30 billion and a llama 7 billion, and you're like, sometimes I want better performance, better accuracy, so I'm going to use the 30 billion model. And sometimes I want it to run a little faster, I don't care about performance, so I'm just going to use the 7 billion. If you want to switch back and forth, basically what you're doing is if you have the 30B model in memory, you're just flushing it. You're completely throwing it away, and you're loading a brand new 7 billion model. In the case of MatFormer, if you have the full yellow model loaded up onto your GPU, you can actually switch to using the blue model without having to throw anything away because you're just going to use the first half of all the weight matrices. And so that's like a slight convenience that you can switch back and forth between higher and lower power, and you don't have to actually load and unload. It is true that if you somehow loaded the smallest one, the red one, and you decided you wanted a higher accuracy, uh, then you will need to load more things into memory because you only have this little bit. But if you load a bigger piece, then all the models that are smaller than it basically come for free. You can use them and get faster answers without having to swap things in and out of memory. So it allows you to scale down really good. You can't really scale up. That still requires you to reload things. How is the loss trained how is the loss calculated when training MatFormer? So the loss function is the completely normal loss function. It's just that in this batch, if I'm using if I did a random number generator and said I'm using all the weights, then it's going to use all the weights and it's going to calculate the next token prediction and it's going to calculate the cross entropy loss based on that. If I roll the dice and it says I'm going to use the 1/8 sized model, then very likely my next token prediction isn't going to be quite as good, and I'm going to have a larger loss. That loss will only ever modify this subset of the weights because that was the portion of the weights that were used to um, to calculate the next token. So everything really is exactly the same. It's just you're sometimes using the full size model, sometimes half, sometimes quarter, sometimes eighth. And at the time that you're using, say, the quarter size model, effectively you just pretend the other 3/4 weights don't exist at all. And you just do next token prediction like normal, and you do loss calculation like normal. But the reality is the other 3/4 of the weights do exist, and in a different batch, you might be using them because you have the half size or the full size model. And that's really the only difference. So uh, I don't have a tab open for, but let me see if do they have the code link at the top here? This might be it. Yeah. Okay. So uh, this is the code for the whole Matryoshka thing. It's only 50 lines of code because basically there's a place in here where um, if you look, they have scale factors of 1/8, 1/4, 1/2, or full size or whatever, right? Basically, all they do, if you know Python slicing uh, um, conventions, is like for this particular weight matrix, it's either let's say the full size weight was 256. It's either saying give me all the weights, 0 colon 256, or it says for the half size 0 colon 128, and for the quarter size is 0 colon 64, and then for the eighth size 0 colon 32. And that's the only thing they change. And so as soon as you just slice the weights and you say 0 colon 32, you're just pretending the other 7/8 of the weights don't exist at all. And they do this at every layer throughout, the whole model. And so yeah, 50 lines of code turns a normal transformer into this MatFormer architecture. Pretty crazy. Cool. Any other questions? All right. So going back to the paper. Uh, so yeah, I thought it was kind of interesting. It's not super clear how much benefit you get from being able to scale down really quickly. Um, for most users, for desktop use cases, on a phone, you could imagine that this could come particularly handy. So let's say the phone only has two sizes. It just has yellow and blue, okay? And it has enough memory, GPU type memory to load the yellow model. So you load the yellow model and the user's interacting with your application, um, and they're doing something complicated. They're asking for medical advice on their phone or something like that, okay? And it's using the yellow model and it's doing everything, okay? And then maybe at some point another app is running and I don't even know if I can think of a realistic use case, but like, you know, it's Facebook and it just wants to basically one of your friends posted a picture of their dinner and it's basically just using some image classification to say, does this look like spaghetti or does this look like pizza or does this look like steak or something like that. And you don't really need super high accuracy. You don't need a lot of reasoning to just say, is this a steak or is this spaghetti? So then to get faster response and use less compute, they could on the fly switch to the blue model. Um, and you don't really have to do anything because again, the yellow model is loaded in memory and you saw it's those 50 lines of code effectively that you just in one place you change it from full size to half size and wham, you just run inference and magically it uses all the blue weights. So I think it makes sense that on a phone, this is something where you can imagine people switching back and forth between this app wants the better model for a medical question, and this app is doing something, again, that it wants AI, but it's just not a really stressful use case. And and so then it can afford to use the smaller model. So that kind of makes sense, like why the MatFormer might be um, something handy for the phone. But here's the really crazy thing. Uh, uh, they said when we train it, we're either going to do yellow or blue or orange or red. But then when they were done training, they started playing around with the model and they were like, okay, every single weight was yellow or every single weight was blue or and so on and so forth. But what if when we do inference, instead of doing it that way, we mix and match. And so you can see, like, here is this crazy thing where they say, layer one, we use the really tiny one, the eighth size. And then layer two, we're going to use the quarter size. And then layer three, we use the half size weights. And then layer four, we use the quarter size, whatever. And what they found was that it actually works pretty well. So this idea of the the smaller weights and the bigger weights being coherent, okay, coherent is probably a pretty good word because um, when they did this crazy mixing and matching, um, things actually um, performed reasonably well. Now, in practice, they said, while you can do anything like this crazy thing where it's eighth, quarter, half, quarter, they're like, realistically, when we did tests and you have very different sizes, it's not optimal. And so what they said is that the most practical examples would be just use two sizes. Okay. And so they're like, the first half of the layers you can do 1/8, and then the second half you can do 1/4. And if you do that, you'll get something that's halfway in cost between um, medium and small. And so you can do this for two reasons, okay? I was talking about compute. Do you want the yellow that's the slowest, or do you want the blue that's the fastest? You could pick a point that's in between, um, but there's another reason why they say this might be something you want. Let's say you do want the yellow, but it's going to require 2 gigs of memory on your GPU to load the full yellow, and you only have 1.8 gigs. Instead of dropping all the way to the blue model that only requires 1 gig, you could do this thing that they're talking about where you say, 3/4 of the layers are yellow, but I have a few blue layers in there to get me down from 2 gigs to 1.8 gigs. And so I think in a world where you have lots of different devices, not everybody has the same phone, right? They might say, "Hey, our yellow model fits just fine on our top of the line um, uh, Pixel, phone, but there's all these other phones out there, and so maybe instead of dropping all the way to the half size model on other phones, you can do this in between uh, sizing kind of a thing." So again, you never want the blue model because it's better performance than the yellow. All of this stuff is about decisions that you need to make because we're trying to squeeze these small models onto phones. So, like I said, the Matryoshka is probably the most talked about, the most interesting thing um, that they did, and so now you kind of have a little bit of background. We've talked about not only how you train it, but also ways in which you can do inference. I do not recommend you do the, super crazy mix and match where it's like, quarter, full, half, full, but they said yes. If you're using two adjacent sizes, then it does allow you to interpolate between the amount of GPU memory you need between the larger size only and the smaller size only. All right. Any other questions about the Matryoshka? Okay. Um, spent a lot of time on this. I'm going to spend less time on these other two topics. Um, a few places they mentioned they do this alt up alternating updates thing in 3N. We don't know the details of exactly how they implemented this in 3N, but we do have the archive paper where alternating updates was researched and it was discussed. So what's in the paper may have been further refined, and there may be some slight tweaks into what's actually happening in 3N. But essentially, what they're doing is they're lowering the compute cost, um, where if the model dimension is 2048, instead of processing all 2048 floats every single layer, um, the cost of doing attention on something that's dimension 2048 is a lot more than the cost of something that's smaller, say 1024. So they use a certain special technique where in the first layer, they'll process the first half, the 1024. In the second layer, they'll process the other half. And then the third, they'll go to the first half and they'll just alternate. So that's where the alternating updates name comes from. They didn't try other things in the paper like thirds or quarters. They just did halves. If you literally did this where you just said, I'm gonna pretend the dimension is 1024 and I'm gonna do odds process the left half and even layers process the right half. If you think about this, you're going to run into a problem where the right half and the left half of your data never talk to each other because any one layer can only see either the left half or the right half. So you need something else that allows them to talk to each other. You could sprinkle in layers that can see both, that operate on 2048. You could sprinkle in some new kind of layer that just does some kind of mixing back and forth. What they chose to do, I don't really fully understand, but they said in the paper that this came from some research on neural networks that were designed to solve differential equations. Um, and so what they do is when a layer is processing only the left half, they do an inexpensive prediction of how the right half is going to modify. So they don't leave it alone, they actually still update it. But they don't update it with attention and the full MLP, that would be expensive. They do something much cheaper to predict what the change should be. Then they also take the final output from the left half and they do another second inexpensive calculation saying, knowing what happened with the left half, let me now do what they call a correction, a tweak to my prediction of how the right half should change. And in particular, it's this correction step that can see the output of running the full attention and MLP. Um, and so when you do this quote unquote correction in the extreme, you could literally copy everything from the left half to the right half. That's not what it does, okay? But if you did do this, you can see how then very quickly you would have mixing of information that's in the left half and the right half. And so I don't have a good full intuition on what's going on in here, but they talk about it's a predict and correct mechanism, and um, that allows it to do cheap processing at each layer, but to have some amount of mixing of information. And so if we look at the paper, I think this is the diagram that shows it well. A regular transformer is doing full width every single layer. And here you can see one layer is doing the left half. The next layer is doing the right half. But again, the half that's not getting processed, that's not light blue, is not flowing through unmodified. It is doing this slight, lightweight prediction. And then this quote unquote corrector, you see, works on the entire full width, and this is what I was saying, where the mixing can happen. Any questions about this alt up business? All right. First time I've seen this, for the MLP layers inside transformers. I think uh, um, by using only half of this, it cuts the cost in half. For the attention layers, I'm not exactly sure how they implement it. I think it cuts the cost in half, but because attention is quadratic, there's the possibility that it could actually be cutting the cost in a quarter or somewhere in between in half and a quarter, but it's at least cutting it in half. So you'd have to do experiments to really see how it compares to have, a 30-layer model that's doing these alternate updates versus a 15-layer model that's doing full updates, or whatever. But obviously the Google team, they found that this was helpful in terms of the trade-off. I assure you, GPT-5, whatever it's called, Plus Pro, whatever, is not doing alternating updates because, again, this does not give you better total performance. This is all about trading compute and performance off. So they're saying we get pretty good performance and we get better performance than just by shrinking the model by doing this alternate update thing. All right, then the last innovation that's in here is this thing called Laurel, Learned Augmented Residual Layers. And if you have a standard residual connection, so this would be like a ResNet in a convolutional neural network, a CNN, as well as all the residual connections in the original Vaswani canonical transformer. The residual connection is you have some layer, and you take the layer output and you add it to the input. This is your residual connection. So for the sake of being clear, we can say it's 1 times the layer output added to 1 times whatever the input to the layer was, okay? Nobody normally says that, but the reason why we're saying 1 times is because we can learn values other than 1. And so what they're going to do is they're going to say this 1 can be some other number. It does not have to be exactly 1. If the layer output is super duper important, then we can actually have the number be bigger than 1. So if we said 3 times the layer output plus the input, that means that it would be upweighting the importance of the layer and downweighting the importance of the residual stream. If we have this number be less than 1, then that means that we're actually downweighting and we're saying, hey, you shouldn't be overwriting, you shouldn't be shouting over whatever information is there on the residual stream, you should be a little bit quieter and your information's still going in there, but it's just not as loud as it were. That's one thing we can do. We can also modify things for the residual connection, and instead of just simply having a scalar multiple for that, they actually um, apply a linear function, so a matrix multiply. Uh, uh, Actually, it's not a full matrix multiply. It's a linear function. It's a scaling, but instead of just saying alpha times the entire residual thing, they're saying it's alpha sub 1 for the first float, alpha sub 2 for the second float, alpha sub 3 for the third float. Kind of like that. If I remember right, that's what this linear um, thing is. So then what a normal residual connection would be 1 times output plus 1 times the input. Now it's alpha, a learned parameter, times the output, plus some function g of the input. So that again gives it a little bit more expressive power at a very tiny weight cost. So if the residual stream is 2048, you have 2048 weights here, maybe plus a bias, I'm not sure, and you have one weight here. So for 2050 weights, you get a little bit more expressive power. And obviously they did experiments and they feel like this additional gives them more boost than if they had just said 30 layers times 2000, 60,000, if they just added 60,000 parameters somewhere else, to the MLPs, to the attention, to whatever. Um, Yeah, so super briefly, if we go to the paper, I think they have a diagram. Yeah, I didn't find this diagram to be terribly helpful. Um, but basically, what they're saying is that you take the output of your layer, and in this blue box, we're doing a calculation. The default would have just been f of x plus our input. But instead they throw in an alpha multiplier here and they say function g that operates on this. They did try some other tricks in the paper, which again, uh, Google has not published the details of what they do. One thing they do is this g function, they do low rank in order to make it a little bit less expensive. Another thing they try is instead of having just a direct residual connection, they say, let's have residual connections from all the previous layers. And in the paper, if I remember right, the having stuff from all the previous layers didn't really help that much. So then they said, well, it's more expensive, so let's ditch that. And so the one I described just a minute ago is just this simple modification of the residual and not using multiple previous layers. All right, cool. So, final chance for questions about any of these topics: Peely caching, Matryoshka transformer, alt-up, or Laurel. All right. Any instead of questions, any comments just in terms of like the effort Google put into trying to get this to be a performant but much smaller model that will run on your phone. I don't know enough about these architectural things like Alt Up or Laurel. I don't know enough to know, oh, why did you use that and not something else, whatever. Presumably they ran a bunch of experiments, but I will say that um, it's been obvious for a while. This will not be the last time people are talking about what it takes to get an LLM, a decent LLM on your phone. Apple has published, different things, what they're doing. They were heavily using LoRa in order to be able to customize the functionality for different use cases. But it's all about we need this thing to be small and we need some amount of flexibility here, so they have like their conditional loading and whatnot. But it looks like Google threw a lot of tricks in their tool chest, a lot of tricks into this 3N model, and so that's what makes it kind of interesting to see. Not just that they scaled it down, like, oh, we'll make that part, half size. We'll make that part three-quarter size. We'll make that part, one-third size. Um, they clearly spent some effort in terms of tweaking the architecture from the full size powered architecture to, again, some of these decisions which, maybe if, affect your benchmark performance by 2% or whatever, but if it cuts the size of the model in half, and you only lose 2% of the benchmark, that's probably a pretty good trade-off for them.
Yeah, I think I mean, there's a lot of interesting stuff, or like the paper is about how to make a small model, fit on constrained VRAM. But at the end of the day, the question, at least for me, is well, a couple of things, I guess. One is like how many of these scale up how much, because if it's more, if I can get more model into the same VRAM, then I can probably use that for perf in some way or another. And then the other thing that this made me want to do is reread the Apple paper
Hmm.
on what they did, because I want to compare like what did and didn't get done in Gemma as opposed to the whatever tricks they pulled in Apple, and then see where the disconnect is.
Yeah. I don't remember there being many architectural tricks in the Apple paper. I just remember they said they used bunches of LoRa's.
Yeah,
So
I remember that being a part of it, definitely part of it. I'm curious.
yeah,
Yeah, I wonder what they
yeah.
did.
I don't know. I don't remember that they said what the LoRa's were for, but like it's not just like text, video, audio. I mean, I'm sure they had those,
Mm,
but uh, it almost felt like this is going to be terrible, but that like there was a medical Laura and you know, a veterinary Laurel Laura and you know,
yeah,
high school history
mhm.
Laura, you know what I mean?
I
That
mean,
was
yeah,
what I
yeah.
felt what I got left with.
That makes total sense to me, honestly. Or because like in my current pet project is kind of like, okay, how far can I push this sort of new wave of open source models? And definitely at the end of the pipeline is there's it's a thing from Predabase called Lorax or LoRaLand. But the basic idea is like you train a ton of LoRa's, you stick them in a box, and then like every time you query, you try to route it through the appropriate LoRa, um,
Hmm.
which in principle is
Yeah.
the same thing. And then the but I'm curious if an approach like that is compatible with any of this. And then I'm also interested in MatFormer specifically because I feel like the Matryoshka embeddings like technique is not something I hear about frequently, and it seemed really interesting when I first like heard about it. So
Yep.
I'm quite curious as to like I probably want to look at the MatFormer paper honestly too. So
Yeah. Yeah, and again, like it, perhaps if you were training from scratch and you knew your phone had exactly this much, could handle this big of a model, right?
mhm.
Then you just set yellow to be that and you train it once, right? I feel like part of the power of their MatFormer is that there are different size phones and you can't and you don't want to do the least common denominator. You know what I mean? You don't want to
Mhm.
have this 1B phone that's the crappiest model, but it'll fit on any phone when somebody else is there running a phone that could have a 5 times bigger model. So I feel like this is a good way for them to say, I built a family of models that can very easily be sized for your particular phone.
That's actually a really solid point, I think, just because so like Apple is going to go LoRa's only, and probably the reason they're going to do that is because they know it's going to run on Apple hardware, and all the Apple hardware is always the same, right?
Yeah, yeah.
But
Even though they have the Pro and the whatever, basically all
it's all coming out of the
iPhone
same factory.
16s
Hmm.
have this kind of a horsepower.
Yeah, yeah. But Android, as we know, is like a wild, diverse ecosystem, and that's
Yeah,
what Google has to play for here. So
yeah,
that makes total sense.
yep. Yeah, and then I don't know when we get down into this like 2 billion-ish range, but in general, for large language models, the the MLP parameters far outnumber the the transformer parameters. So if you could shrink your MLPs and use LoRa's, that could shrink your model a lot because
Hmm.
that is the bulk of your weights. That's the
Right.
bulk of your memory need. And so if you had a smart enough router to say, oh, this is a question about history, let me load the history LoRa. Oh, this is a question about medical, let me load the medical LoRa. You may actually be able to get surprisingly good performance from that tiny model because effectively it's if you add the sum of all the LoRa's, you know what I mean? It's actually a much bigger model. It's just clever enough to partition its weights into only using this part at this time and that part at that time. You do need a really good router because what happens if somebody asks you a historical medical question? Now what do you do? You know, whatever.
Well, I mean, end of the day, like your MOE is always going to live or die by your router quality. So the first thing
Right.
you need to figure out anyway is the high quality routers. Although the I was just,
Yeah.
I'm like looking at the abstract of MatFormer, which is
Hmm.
like we show that an 850 million decoder only allows us to extract multiple smaller models, um, which
Yeah.
wasn't really how this was. I was framing this in my head, but between taking a large base, extracting a smaller model out of it, hooking that up with the correct per query LoRa, I feel like you could save like a ton
Yeah.
um, uh,
Yep.
doing
Yeah.
that.
Just know that in regular MOE for frontier level models, um, the routing is done per token per layer. And
Hmm.
in Apple, the routing is being done once at the very beginning,
Yeah, that's
fully
a
partitioned.
good point.
So it's actually no. Yeah, it's being done once per input. It's not even being once per token. It's just
Hmm.
once per input. So this question is a history question, and I'm
Yeah.
going to give you these LoRa's. So it's a very, very different router. It's a much in some ways it's a much harder problem
Hmm. I'm
because
curious to see like are what is it even appropriate to call those things the same thing, right? Because it's like
yeah,
one is going, one is feels like a kind of a deeper part of the architecture, and it's grabbing experts per every single token, whereas this really does not, or like this kind of routing doesn't feel like that kind of routing, at least to me.
yeah, yeah,
Sure.
yep, exactly. So yeah, at first I was even avoiding using the word. I was just saying heavy LoRa's and not.
Hmm.
But yes, you're right. I think we probably should try to avoid using the same router word because they're really doing very different things.
Hmm. I noticed at the end it didn't use the term Laura, it said Laurel or something. Is that part of the
Oh, in
notation?
this?
Yeah,
No, no, this is different from Laura. This Laurel thing is
Laurel.
just
Okay.
this residual, um, making the residual connection more complicated to give it a little bit more horsepower.
Okay. Yeah,
Okay.
I was just looking that
Now,
up yesterday on the
you can
because on
get confused because they actually did do a low rank
the
version of Laurel. And so if you look in the paper somewhere, they say, here's our low rank. And they
oh
called it
God.
LR to make it not
Okay.
confusing. But if they called it a Laura Laurel, then that would have
We
just been,
we have a
we would have
router
been,
that's not a router. A
Yeah, yeah,
Laura that's not a Laura and a Laurel
right.
that's also low rank. Yeah,
So thankfully, they didn't actually say Laura. They just said hyphen LR.
yeah.
So that was actually my question. So when you're talking about a LoRa, you mean a fine-tuned, quote unquote expert that is, statically routed at the beginning, and it functions like an expert, but it's really just a fine-tuned model using LoRa, low rank, whatever it is.
Adapters. Adapters, yeah. Yeah, so
Okay.
basically what they said is there's no blue, there's no orange, there's no red, there's just yellow. Okay? And there's yellow prime that we use when it's a history question. And there's yellow double prime that we use when it's a math question. And there's yellow triple prime we use when it's a Spanish question, whatever.
I wonder.
Okay. And so, but because of the nature of LoRa, if you're familiar with it, it's relatively cheap to swap them in. You're not paying the cost of fully swapping out your model and swapping in a new model. Okay. So it is effectively a completely different a yellow prime, but because of the way they do it, it's a little bit cheaper than
So it's about,
memory wise, bandwidth wise.
yeah, so it's fast because you're just fine-tuning a sparse subset,
Yes.
and it's just that subset that has to swap in and out.
Yes. So conceptually, instead of doing something like blue, you're completely replacing the yellow, but LoRa does allow them to do it in a bandwidth reasonably efficient way. So when I was saying the good news is if you go between yellow and blue, you don't even have to update memory. You can just use the blue half and then go back to the yellow half for your next app. Apple's approach to having multiple apps having different needs is that you can you can just swap the yellow prime LoRa, and that's relatively cheap. It's not zero like with blue, but it is relatively cheap.
It's a lot cheaper than the mixture of experts memory explosion that everybody complains about.
Well, I was a little bit surprised that the GPT OSS that came out was a mixture of experts MLP model. So clearly, this OSS model is not targeted for end users. I mean, the size of it, 20B, 120B, is also an indication it's a little bit too big. But mixture of experts is not beneficial when you're running it on your laptop because it
Don't have the memory.
it does less compute, but it actually requires a lot of GPU memory to store all these experts.
Which is I'm sort of bumping up against that right now, where it's like the models that I want to deploy are, maybe they're maybe going to serve like 20, 30 people. So like it's reasonable to grab some H100s, but it's like if I want to load up something like Kimmy at a trillion parameters, it's like, okay, there's
Yeah,
no way for me to make this make sense unless
no.
I have like, 1,000,
Kimmy makes sense when you have multiple users that are sharing all those experts. Yeah,
yeah,
yeah. I
exactly.
can't remember which family I was talking about. I don't know if it was Quen or something like that. But basically, you saw it was like the really big one, right? Was like hundreds of billions of parameters and it was MOE. And then the next biggest one was, 70 billion and it was MOE, whatever. And then at some point it drops down to 30 billion or whatever, and now it's no longer MOE, it's dense. And the 7 billion is dense. And it's exactly what we're talking about here is that you're assuming that the hundreds of billions models are meant for a server enterprise kind of a situation, but the 7B is meant for single user, and so MLP MOE does not make sense
Which is
for a
very
single user.
strange because I feel like at least for the 20B, they kind of made a big fuss about it like running on consumer hardware where it's like,
Right.
okay, like I have like 17B extra parameters here that are just kind of lying around. So like could you chop those off maybe?
Yeah, that's why I was surprised that
Mhm.
that GPT OSS was mixture of experts.
I wonder why that because I did we go over that paper yet? I don't know. I feel
GPT
like
OSS?
I think I did in my Wednesday club. I
I
don't
was
know if
gonna
you did
say
it. Yeah.
it came out 2 days ago,
Yeah,
so
well,
I
yeah, no, we did it same day, I think. I believe on Wednesday is when we did it.
yeah.
But it
So
was the other I think it was because I was looking up dimensionality of residual streams at the time because the I think it was the 20B that had like 2000 um
2048. It's the same
yeah,
size as Gemma 3N that's supposed to run on your phone. It's
right, which
I
was
think
so
that's
weird.
a little surprisingly small.
Yeah, me too. Because I actually wasn't the question that occurred to me there was like I don't really know what the standard dimensionality should be for your residual stream based on your model size. So I was looking it up and it was like comparatively like really small. Like the the 2K was like 3B to 8B range, and that's at on a 20B, all of them were like way at least double that.
Yeah,
So
somebody's already fine-tuned the 20B unslotted and as far as what that into GGUF. So that gets it down even further. And I think that you'll start to see fine-tune 120Bs. I know 70B was a common model, but like the 400 Llama B was kind of outside the reach of fine-tuning for a lot of people.
Yeah, but no, but we're specifically talking about the architecture here. We're talking about the residual stream, and let me just see. Uh,
I think I did a couple of searches on it
yeah,
yesterday
yeah, yeah. I'm
at
just
averages. But I remember it being like that number,
yeah.
like because we were sticking on it for a while because it was like, okay, this is kind of weird, but I don't know exactly why.
So Llama 370 billion is 8,000. It's four
Yeah.
times as big as GPTOSS.
Mhm.
So
I don't think this is a fine-tune that I put in the chat. They're just reducing the size to
Mhm.
GGUF. And that's like the practical format that most people use for like phones.
Can you,
yeah.
when you're working with an MOE, I'm wondering if it's like, if I'm not serving that many people, is there like a way to kind of take advantage of the sparsity when it comes to quantization, maybe, and try to fit it on something lower? But I don't,
Not that
nothing
I'm
comes.
aware of, which is why like I I will whatever like rail on you shouldn't build these small MOE models.
Yeah.
So
Well,
I don't know why they did the 20B as MOE. It just doesn't make sense to me.
it's
Um,
very, it seems to be very trendy right now
yeah.
as well, which I'm not
The
entirely.
one thing I will say, well, it's possible it's MOE if they somehow distilled or did some, if they somehow needed the two of them to be similar architecture for some purpose. Um,
Hmm.
but OpenAI also has this weird problem that they want their open source model to be good so that people are talking about OpenAI instead of just constantly talking about Quen and DeepSeek and whatever. But they
Hmm.
don't actually want it to be as good as it possibly could be because they don't want it to compete with their paid model. So they're
Yeah,
really in my opinion, they're really threading a needle here.
well, and it was very like except for the like few extremely weird decisions, the like it was a very like kind of bog standard kind of architecture from the read I got from the paper at least. So
Yeah.
that kind of tracks to me.
I mean, they
Well, I
don't
think
want
the
to give
biggest,
away their secrets in their
Right.
open models. So,
yeah, I think the biggest issue is in a couple weeks, these are at least the 20B will probably be out of date. And that's why I say then people start fine-tuning this Apple one. And the other question is like performance wise, is it there? Because Chat or OpenAI was saying like it's close to O4 mini
I was
performance.
not having that experience at all when I was running it the other day. It was, yeah, it was not pretty.
Yeah, I've heard
yeah.
pros and cons. There's the AI Daily Brief that I listened to. His first one was more positive, and then the second one, it kind of mixed reviews on that. But performance wise, I don't see them being. That's how fast these things move. Like Quen or probably not Llama, but Quen or the other one, they're going to come out with a new model in a couple weeks.
Well,
So
Oh yeah,
then you have to
yeah.
fine tune these ones.
Yeah, I
It's
mean, even if you try your hardest, there's a decent chance that next week somebody's going to come out with a model that's better than what you did. But OpenAI clearly did not try their hardest on these open source models.
I
So,
I remember seeing I saw a post that was I think it was the 20B or something, that they trained it for like 500 grand, which is an unusually like small amount to train. And then like one of the people that works at OpenAI was sort of pointing that out, like, hey, like we can do the DeepSeek thing too, except like when I'm using either one of these models, it's I I don't know, it could just be the way that they're serving it or something, but like it would like for even like a single prompt that's under 32K tokens, it would like it would start, if you try to get it to like describe a particular like narrative or scene or thing, like it does the thing where it forgets about the spatial reasoning of the location in which you're trying to get it to describe, like almost immediately. And that was on the 120B, which was like, to me, it was like, okay, I don't like switching back over to Qwen 3 instruct, which to be fair, double size of the model, but
yeah.
there's no possible reason why I would ever use the 120 over the Quen instruct, at least the most recent one.
Well, that's disappointing to hear, but for me, at least, not terribly surprising. I mean, I can't imagine that OpenAI really put that much effort into their OSS model. You know, trying to
Yeah,
tick a box.
positive is they're American models. They're Apache too, as well. And I think the others, Quen and the other ones, like they're MITs, but they're American, right? So there was this issue earlier this year with DeepSeek and how exactly was the model trained. And I saw something in the government, like even not allowing them to make new models. So I think that's a huge thing if you're an industry, is that this is an American model. It should be, it says Apache 2.0, so pretty much open source. And I think people will make better use of doing things with it, because of the American model.
Yeah,
yeah,
maybe.
that,
I mean, yeah, the paid models are costs are, keep going down too. So, uh,
yeah. I just pulled up my chart again. GPT 3, like not even 3.5, at 2.7B is 2,500 dimensions on the residual stream, as opposed to this
yeah,
20B MOE that's
yeah,
like sitting at 2K, which now sort of, after kind of looking into the residual stream, like now it sort of makes sense why it's just like immediately starts being incoherent, just like it just doesn't have the bandwidth to keep anything between these weights, essentially.
yeah. I don't even really know how to comment on a model that, right? They knew that within a week they were going to announce GPT-5 when they announced GPT OSS, right?
Right.
It's a model that is knowingly much worse than what they're capable of building. I don't even know how to comment on that.
And it's strange because the benchmarks for it, like they were kind of hyping it up. They were like, yeah, this is, we're this thing's a real player. So I was excited, and then just like running it through
Yeah,
any bench that that I'm familiar with. Like the only way it could have passed any of those benches is if it trained on the directly on the bench and it was in distribution. And even then, I'd still be surprised.
Yeah, another thing to consider too is the open source models, they're not updated that much. We saw the R1 being updated, I think one major one, but if there's bugs or like minor stuff, even most manufacturers are not going to take the time to fix it. But the proprietary models, I know for at least 4.0, and I could just imagine O3 and now GPT-5, is that they take time to improve the models while it's that name. So you get better performance over the course of its lifespan. And there was a study by Peter Gostov, he's AI Moonpig, something like that. And he said he posted all these benchmarks for 4.0 since, plain old GPT 4.0 since last year. That was May 2024. And then he'd do benchmarks on the same model over and over, and it kept improving over the course of its lifespan. And then they add features like deep research, more PDF uploads too. So that's another thing too with the proprietary models, is that they see a lot more attention. They don't just get
Sure.
dumped on the web.
Sure. Yeah, and I mean the other thing is even though they didn't change the name 4.0, I do think that the model
Yeah.
changed. It was not
Yeah.
just that it was trained on a little more data or something like that. Yeah, the vibe that I got, and maybe I'm just totally I could be way off base, but that basically OpenAI wanted to say, now that we have GPT-5, I will
Yeah,
open source my
exactly.
2 generations ago model.
Mhm.
I will open source something that's GPT-3-ish. Okay?
I think you're spot on there actually
Right.
because of the training cutoff.
Yeah.
It's the same as GPT-4. It's the June 2024 or
Yeah.
whatever it is. It's the
But
that
but
stuck
but
out.
the other thing is I think that that goal got somewhat, I don't know what the right word is, derailed. Because had they actually done that, it would have been too bad. It would have been too poor of a model. So I think they had to last minute try and
Oh,
jam a little
sure.
bit into it so that it didn't look so embarrassingly bad compared to
Hmm.
Quen and DeepSeek and these
I
other open weight
wonder
models.
I wonder if because so 20B MOE, I think it's around 3B active, and if but it has the dimensionality of a 3B model. So I wonder if it was kind of sort of a last minute, like, let's slap this in some more experts and call it a day, like
Yeah, yeah,
situation.
I would easily believe that there was just some last minute things to kind of pump it up a little bit, but in its heart, it's really just kind of a, you know, 2+ year old model. It's
Yeah.
nothing to write home about. All right, guys, I'm gonna stop the recording here, and Jerry may not actually keep all of this.
Oh yeah, we did have a yap as
We
as
did.
we
That's
do.
okay.